Sorry, we can start with a new session with Mark Drakos speaking about the European spallation source for neutrino beam, of course.
Yes, of course, for neutrino beam, and mainly for CP violation. So we continue what we have started this morning with this long baseline experiment. So this is a long baseline based on the European spallation source, which is under construction now at Lund. So it's a European project. So what can we do if we have 5 megawatts proton beam, which is a huge amount of protons? We saw this morning that we could have probably up to 1 megawatt. Here we'll speak about 5 megawatts, which is much more protons. 2 GeV energy, 14 hertz repetition rate, which give us about 10 to the 15 protons per pulse. And we can collect more than 2.7, 10 to the 23 protons per year. So in order to produce a classical, let's say classical conventional neutrino beam, we send these protons on a target. It's so easy to say, but it's not so easy to realize. And we can have also a horn after that to focus the pions, which will decay and will give us our neutrino beam. And of course, at a certain distance, we can place our far detector, and nearby we can place also a near detector if we want to reduce our systematic errors. So we will use these protons in this direction. So after that, what can we expect from this proton beam, 2 GeV protons? This is what you have here for the neutrinos, in case we send a positive current in the horn or a negative current here for the anti-neutrinos. This is what we can collect per square meter at an arbitrary distance of about 100 kilometers from the source of the neutrinos for 1 year. 1 year is 200 running days. So here you have the proportion of each species of neutrinos we can have from this beam. You see that we almost have a pure nu-mu beam. It's 98% nu-mus. But we have also some contamination from anti-nu-mus nu-e neutrinos. It's not a big problem for us. Probably it could be also an advantage because we can use this 0.5% of nu-es to measure the cross sections of the nu-es at the right position where we are interested for the right neutrino range, using a clever near detector. And we can have a good sample of nu-es to use. So this is the probability oscillation probability from nu-mu to nu-e. We have already seen this formula several times. I will not insist on that. We have just 3 terms: the atmospheric and solar, and the interference term containing the CP violation parameter delta CP. So we are interested for this term here than for the other terms, and we want this term here to dominate the other terms. So Sylvia has already shown something about that. Before 2012, before we measured theta 1,3, it was believed, I don't know why, that theta 1,3 could be very, very small. In this case, it was better to go, for example, theta 1,3 at 1 degree, it was better to go to the first oscillation maximum, where the interference term, the red one, was dominating the other terms. But now we know that the theta 1,3 is not so small. For the present value, it is better now to go to the second oscillation maximum here than the first oscillation maximum, because the interference term dominates the other 2 terms that we will induce you some systematic errors. So you expect to be less sensitive on systematic errors on the second oscillation maximum than on the first oscillation maximum. You can also see here that the curves, they are more expanded now. This is for minus 90 degrees, 0 and 90 degrees. They are more expanded on the second oscillation maximum than the first oscillation maximum, because simply the asymmetry here is for the first oscillation maximum is about 0.3 sinus delta CP, while on the second oscillation maximum is 0.75 sinus delta CP. So you are more sensitive to delta CP, and you are less sensitive to the systematic errors. So of course we have to place our detector, as I said, at a certain distance. We can go to the second oscillation maximum if we place our detector at a distance of about 500 kilometers from the neutrino source. And which kind of detector we can have? We can have a Cherenkov-like detector. We can take, for example, the Hyper-KO one we have seen this morning, but there we propose the Memphis one already started by the European project called Laguna. And of course, we can have also the rest of this astroparticle physics program, as we have seen also for Hyper-K or for LBNF this morning. Proto-decay astroparticles can observe also the supernova neutrinos. The supernova relic neutrinos also, solar neutrinos we can also use, and the atmospheric neutrinos, probably we can use atmospheric neutrinos also to attack the mass hierarchy problem if this problem is not yet solved, but we don't insist on that because we believe that the problem will be solved by then. So this is, if we place our detector at 500 kilometers, this is the kind of distributions we will have for the neutrinos after oscillation. We see that we have, we are dominated by the nu's, the new mu's oscillating to nu's. We plan to run 2 years with neutrinos and 8 years with anti-neutrinos to have more or less the same amount of neutrinos, about 200 per each at the level of the far detector. The drawback is that we have low energy, relatively low energy neutrinos around 300 to 400 MeV, and the cross sections, they are not very well known at this point, and you see that they go very rapidly down. But as I said before, we can use our NUI contamination we see here to measure also the cross sections in this region here, because we'll have a lot of NUIs at the level of the near detector. So how well do we cover the second oscillation maximum with this beam? You see here the probability again, and you see these curves for the normal and the inverted hierarchy. You see that they are not so distant, so we are not so sensitive to the hierarchy. And but you see that our neutrinos, the NUI spectrum here, well covers the second oscillation maximum. The first oscillation maximum is here. So we are almost exclusively devoted to the second oscillation maximum. So in this case, what is the performance we can have? Here you have the fraction of delta CP we can cover versus the number of sigmas we have. For the nominal systematic errors in blue, which is 5% systematic error on the signal and 10% of the background, you see that we have reasonable assumptions and not 1 or 0.5% of background of systematic errors. And you see also what we could have if we reduce by factor of 2 our systematics. You see that we gain a lot, we gain something, but not a lot, because we are not dominated by the systematic errors. We are more or less dominated by the statistics. If we double the statistics here, if instead of running 2 years, we run 20 years, there we significantly increase our performance. Here, if we stay with the nominal values, we are at about 50% delta CP coverage, while we can go up to 60-62% here. So where now can we find all these protons? Because it's, I said to you, it's a huge amount of protons. We can go to the European spallation source. Here you see these 3D drawings, very realistic now 3D drawings. You see the city of Lund here, and Malmö somewhere here, somewhere there is a bridge going to Copenhagen. Copenhagen, so the airport is about half an hour from there. So we are interested for this LINAC they have here. Here they have all their stations, the neutron stations. This is what we have here. So ESS is a consortium of 17 European countries, what you see here, who are financing now the construction. They will finance also the operation of this facility. As I said, it's placed at Lund, just on the other side of Copenhagen here. And you have a lot of applications going from biology up to solid physics and much more on that. You see the LINAC here, and they have about 20 or 25 neutron stations all around this facility. Their target is a massive target absorbing everything, which is here at the emitter. So they have a lot of radioactivity problems, but they solve them, and we will have similar problems also for the neutrino beam. So this facility costs about 1.85 billion euros. So as I said, you are very interested about their LINAC they have here. So with this LINAC, we can go up to 2 GeV protons. but there is still empty space there for possible upgrades, so probably we can go up to 3.5 GeV in the future. So they kept this probability to increase the energy of their beam. So we'll have 5 megawatts average beam power, 125 megawatts peak power inside one pulse. They have the repetition rate of 14 hertz. What is not very good for us is the duration of the pulses is 2.86 milliseconds. So we have to reduce, I will show you after why we have to reduce these pulses to few microseconds. So in each pulse, we can have 10 to the 15 protons. And as I said before, we can collect more than 2.7, 10 to the 23 protons on the target per year. So this LINAC will be ready by 2023. It's not something which has to be approved or something hypothetical. The construction has already started, and by 2023, we'll have the full power and full energy of this facility. So how now to add the neutrino facility on top of the neutron one? The first condition is that we must not disturb at all the neutron users. So what we would try to do, we profit of the fact that the duty cycle is only 4%. So this LINAC is almost empty. So we would like to just double the duty cycle and just double the frequency of the LINAC, going from 14 hertz to 28 hertz. So we don't increase by factor of 2 the instantaneous power, but just the mean power. So as I said to you before, the 2.86 milliseconds duration is not good, so we will try to have a few microseconds, even less if it is possible, because we cannot send in the hadron collector huge current for so long, because it will burn this horn. And so for that, we need to add an accumulator here, a small accumulator with a radius of about diameter of 143 millimeters, so we can locate it somewhere here. But also we need to go from protons to H minus, because the protons already circulating to inside the accumulator, they will repel the protons coming to inside. So we need to accelerate now H minus and strip the H minus at the entrance of the accumulator. So nearby we can also place the station, the target station, and the decay tunnel. So we'll see that the decay tunnel is very short, and probably somewhere near detector inside the already allocated area to ESS. So we can have about 300 MeV neutrinos. This is what we see here in red. I compare it with what we would have at SPL, because Carlo has spoke about SPL yesterday, which was one of the possible injectors of the LHC at CERN, but in 2010, CERN has explained us that it wasn't anymore in the strategy of CERN to have these new injectors. But in EuroNew, for 4 years, we have studied this possibility here. We see that the spectrum is more or less similar, so we can use the development we did in EuroNew and inject it in this new study here. So we took everything from EuroNew, the target station, the tunnel, and all the optimizations we did there. And as I have seen before, the detector would take the one proposed by Laguna. So short pulses also can allow for DAR experiments, decay at rest experiments. This is a plot I took from SNS. SNS has similar neutrino distributions also. We can take the neutron target now with short pulses. We stop all the pions there. They will decay at rest. They can give you monoenergetic neutrinos here, but also the muons coming after. They can give you also these distributions there in order to measure the cross-sections for the supernova neutrino as we see here. So there is some overlap between the two. We can also use these neutrinos to do sterile neutrino searches. This is, let's say, byproduct of this facility. So as I said before, we have injected the experience we got from all these projects in the past inside this project here. For example, for the target here, we took a packed pellet target, small spheres of few millimeters, in order to be able to cool this target here, because we have this high power. And we use 4 targets and 4 horns in order to mitigate the effect of the 5 megawatt proton beam. So we circulate inside the target gas helium to cool them down. So we have put in EuroNew that this was feasible. For the decay tunnel is about 25 meters long. It's very short decay tunnel compared, for example, with CNGS, we had 1 kilometer. So it's easy, for example, to circulate helium here and avoid any problems with tritium production or so on. So we have also studied how to replace the system here in case of any problem. So again, all this has been studied in Euroneum, and also all the radioactivity problems. Now for the location of the detector, you have here all the sites already studied by Laguna. But we have studied by ourselves these two mines here, Zigruvan here and Garpenberg there. There is also a third mine which could be also of some interest for us at 500 kilometers here near Oslo in Norway. So Zigruvan is 360 kilometers from Lund, and Garpenberg, the most promising one is of course Garpenberg at 540 kilometers. We have some negotiations already with this company there. In order to optimize to find the best position to place the detector, we have studied the fraction of delta CP we cover. Here is for 5 sigma and here is for 3 sigma versus the distance. We see our Zigruvan is here and Garpenberg is there, so the best is to go somewhere in between. Zigruvan is better for 2 GeV protons. Garpenberg is better if we go higher than 2.5 GeV. I recall you that with the LINAC there is a possibility to go up to 3.5 GeV. So we can reach up to 60% coverage, delta CP coverage with this facility at 5 sigma. Again, with these systematic errors of 5% and 10%, we have some sensitivity also to the mass hierarchy, but as I said before, at this moment this problem will be solved. If we go at 3.5 GeV, we can exceed 5 sigma. But of course, even with 2 GeV, we will start with 2 GeV, probably can exceed also 5 sigma if we use also atmospheric neutrinos. So we have published this paper in this US NOMAS process in 2013, where you can find some comparisons with the other facilities. Sylvia has shown this this morning. So you can find this paper here. This is one of the comparisons that Sylvia has shown, where we have the fraction of delta CP versus the accuracy we can have on delta CP, and we are here. Here we are, the only facility doing better is the neutrino factory there. So now we have submitted last September a project in the European Union in the InfraDev call for design studies. We had 11 institutes inside this application, and we got a score of 30.5 over 15, 5 over 5 for excellence, but this was not enough for them to get finance. We were just below their thresholds. Nevertheless, they recognized that ESS and USB answers one of the priorities defined in the European strategy for particle physics, and this we will use in the future to get some financing from other sources. This is what we are doing now. There is a discussion soon in the Ministry of Research in Sweden to discuss this point. So ESS has started the construction. Here you see the groundbreaking ceremony, the 2nd of September. We see here the two ministers, the Swedish one and the Danish one, starting digging. They did it well because one month after we can already distinguish the LINAC here and all the stations around there compared to this 3D drawing you see here. So they are going very, very fast. Now in February we have here, we distinguish the tunnel of the LINAC already here. And the first proton beam, as I said before, it will be in 2019, but the full power and the full energy will be by 2013. So this could be our implementation of the neutrino facility here with the extraction of the LINAC there, the accumulator and the near detector here. So I'm almost done. As Carlo has shown yesterday that he was needing a lot of muons from the SPL, but as I said before, the SPL is not yet approved. He can find a lot of muons now also in ESS. This is what we have at the level of our beam dump at 25 meters at the end of our tunnel. You see there's 4 spots here of muons coming from the 4 horns and the 4 targets. If you just take 1 square meter around here, you can have 4.2 10 to the 20 muons per year. So we can use it to do a lot of other projects. R&D, for example, the 6 the muon ionization cooling to start to do all these studies for the muon collider. But also we can use it to do a kind of mini low energy new storm, and we can also measure again the cross sections of the new mu and nu using this facility. So conclusion is that it is better to go to the second oscillation maximum. We are less sensitive to the systematic errors. So we can, as I have shown you before, we can consider 5% on the signal, 10% of the background, which is very reasonable. The ESS LINAC will be ready in less than 10 years from now, 2023. The neutrino beam there is very promising. We can reach up to 60% delta CP coverage. Of course, our large detector can do also the astroparticle physics program of all the other huge detectors. And there is also some complementarity with the other baseline experiments. For example, if we take the LBNE, with using liquid argon, we use Cherenkov detector, and we are at the second oscillation maximum while they are on the first oscillation maximum. Thank you.
I don't know if I'm wrong, but I heard that you have been, not endorsed anymore. I don't know if it is because there is some mismatching between your study, your schedule, and the ESS construction, for example. This was a critical point also. So yes. The project had to be decided, approved, studied, worked out before the real starting of ESS.
Yes, for this European application we had at age 2020, I have to say that we are in competition with FCC, which was the first priority of CERN. So, and this probably was the main reason why we didn't get funding from there. But yes, we are continue trying to have a political support. This wasn't so explicit up to recently because the Swedish government and ESS had the pressure to assure the funding for the neutrons. But now they are much more relaxed since last September. Unfortunately, it was also the moment where we have submitted this project there. We got a supporting letter from the ESS director about that, but we want them now to be more explicitly for this project, and I believe that they will do it now because, as I said, they are more relaxed now.
About the direct mass measurement of neutrino, of course. Mettilo qua. È così. Grazie.
Okay. Good evening. Sorry, good afternoon. I will try to make a status of what is considered the search for neutrino mass with kinematical methods. Probably most of you know this. Since we have the paradigm of flower oscillation has been fully proved, a remarkable increase of interest in investigating direct absolute neutrino mass scale is grown continuously since this year. So the absolute scale of mass remains now today an open question, and so experimental investigation from both particle physics and cosmology are now under progress. We expect that in the next decades, a number of proposals, ideas, projects from both disciplines will aim to test the mass scale at very low limits, means at the limits of delta m square proved by oscillation. So after the discovery, we can say that discovery of finite neutrino mass, we can say that now we are going on to imagine a precision measurement, a precision experiment. So maybe you can better focus on this precision experiment statement in the next slides. I will focus obviously on few arguments. I apologize if some argument will be skipped and some project, some idea will be not considered here. Kinematical methods are well known, are based on the fact that beta decay, double beta decay, and cosmology can test neutrino mass in different way. The first can test neutrino mass as a superimposition of the state, eigenstate, and the second one provide the value that a superimposition eigenstates plus a space, a factor due to imaginary phase due to CP violation. And the third one measure the neutrino mass, the full neutrino mass of all species in the universe by weighting, by considering the effect, the imprinting on the evolution of the universe due to this small but important part of the energy of the universe. The cosmological constraints, I give you some overview, are based on the fact that neutrino mass gives some effect of the first at high zeta in temperature and polarization isotropy, give effect on large-scale structures of the universe, or power. This is called power spectrum, mass power spectrum of the universe, at different stages of the evolution of the universe. There are many arguments that can be considered here, but I would like to summarize those arguments in the last prediction, last result obtained by Planck. This is a beautiful image of the Planck satellite, and on the publication of Planck's of results of cosmological parameter from Planck, taking in consideration the results of cosmological fluctuation, plus all the external, like lensing and external data, like power spectrum of matter, you see that the neutrino masses now can be constrained to value of 0.7, 0.2, 0.4, 0.5, depending on which model we consider. This is aspect is one of the peculiar aspects of the measurement of neutrino mass by means of cosmological data. The future, respect to the present situation, respect to the Planck. Is it possible to the present limit, to go further in the present limit if we are able to measure the microlensing of the cosmic microwave background? Microlensing of cosmic microwave give a possibility to go deep in the sub-eV range, a level of 10 to minus 2 eV. This is typical aims of the mission, so-called polarization CMB missions. This can be considered the next future for cosmology to improve limits, improve constraints on neutrino mass. My consideration about the cosmological constraints is this: it is true that the neutrinos are a small fraction of the matter of the universe, but for peculiar consideration about nature of neutrino, they have some contribution. It's not huge, but some peculiar contribution of on the cosmological scale. chronological parameters. They are decoupled relativistics. They are made the transition from relativistic one to non-relativistic velocity late respect to late times respect to the Big Bang. But if you consider all the data, you have to take care because there are tensions among the set of data. There is a tension mainly due to this set of data are mixed data that are not fully independent. So correlation must be taken account. It must be taken account in a very careful way. The question is that we have seen the constraints depends on the model used. So the next generation CMB mission have to improve the sensitivity, but also to improve this problem of modeling of the CMB. But when you go further in sensitivity, the small correction that are now present becomes the main corrections. The main correction to be done. So that this huge correction to be done can be very important in the next future. So this reason, for my consideration, I think that cosmological constraints are very important, wonderful data, but direct searches laboratory are needed. That's the final conclusion. We go directly on what the community of direct neutrino mass measurement are doing. The main experiment now is in fabrication phase. In final phase of fabrication is scattering that use the largest source of tritium in the world and provide in the transport section a source of electron emitted by tritium that pass through all the section and go in the main spectrometer in which they are selected in impulse and measured. I don't give because there is Philip here that will give in the next talk more detail on Catherine. Another important project based on this technology, this is Project 8. Project 8 is based on fluctuation, on measurement of the cyclotronic frequency of the electron that in the magnetic field, electron emitted by tritium, that in the magnetic field moves with some special antenna, they are detected. This is the first detection of this kind of electron, beta electron emitted by tritium, by Joe Formaggio, send an email to the community, very excited for this result. That I consider the first step for the future technology beyond scattering. But what has born more than 20 years ago, when the experiment on tritium were established since many years, is the calorimetric measurement. The calorimeter, most of you knows how they work, is a typically system which the isotope is embedded in the mass, and you measure the temperature of the changes of this mass after the decay. So you have a pulse. But to measure this teeny temperature variation, you have to go a very low temperature in which the specific heat of the material is so low that you can disentangle this change from some thermal fluctuation of the system. This is ideally an energy dissipation spectroscopic detector. This is a full system that will take care for all the energy emitted by a radioisotope, except for the one released by neutrino. They are quite fast, not so fast. That means that the fastest calorimeter are 0.1 nanosecond rise time, one few microsecond rise time. That's an important parameter for taking fast acquisition. And sensitivity sensitivity means resolution are now presently at the EV scale. So those detectors can operate on temperature, have to operate at temperature from 10 to 100 milli-K. And in principle, this technology has been tested since many years, and is a technology that will really provide a tool for go deep in sub-EV range. This is some slide that I show many times. This is just to show that this technology has born practically in late of 80 years. This is probably you don't see very well, but it is a number of people that in Paris at the bistro signed the first community agreement to work on this field. At that time, they worked mainly on double beta decay, dark matter problem. You see Spillantini, Vitale, Barone, Stodlowski, Ninikowski, and so on. There are a few people. 1 year later, this was the first meeting of this community. It is the meeting in 2013. This year will be the LTD 16, in which the community will in Grenoble. The community will group together in Grenoble. So now we are hundreds of people working on these detectors, and the technology as now considered a mature technology. What I would like to now to skip a little bit something go to one of the projects that are funded by ERC, European Research Council, and based on the idea of the Rucola and Lusignoli of 1982, in which they proposed to test the neutrino mass with normal kinetic methods at the endpoint of this electron capture decay. So this first measure has been made by this first test calorimetric with a calorimeter that is made by me in 97, sorry, and so since 97 we have very bad results. No, I don't show the results very bad. I would like to avoid to show, but just we have seen the spectrum, but obviously not at this level. Since 97, we work a lot using these isotopes, and also another isotope, rhenium-187. This is another candidate. On both, we have worked a lot. This project has been funded, has been proposed and funded last year, and started. This project is a project of INFN and ERC inside INFN. Those are some statistical prediction of the model of this experiment, in which you see that depending of the Q value that is not well known and the statistics that we can acquire, we can cover almost the 1 to 0.1 sensitivity range. There is some interesting approach also for search for heavy neutrino. This is a simulation made by Angelo Nucciotti of Milano, in which you see that it's possible to also use this complicated spectrum to search for kink for heavy neutrino from few EV to key EV regions under EV. The project is not so simple, so we are not ready to start with measurements. We are in final R&D phase. Just to explain how the project will go on, Presently, we need Holmium-163. This is not in nature. We had to use erbium-162 with neutron irradiation to produce 162. We use this powder. This very this powder cannot be used like you see. This powder must be put in a reactor. You have a powder of this kind, this pink powder with holmium. Later on, we have tested using this powder that we see some spectrum. This is not calorimetric, but just to test, put on the detector that some holmium has been produced. But looking for, in some way, we have found a method to take this power and this oxide and produce metal. This is a metal holmium produced by this powder, making a reaction with yttrium and distillation. So we have produced, and metal is very important because our detectors are made with metal. So what we want is to put metal holmium 163 inside a metal matrix and don't have any kind of oxide or different molecule that can change the Q value by molecular effects at level of EV or less. Otherwise, if you have several compounds, you have spreading of the Q value due to different configuration inside the molecule. The detector are the one you see below. This is so-called TES detector on a silicon nitrogen membrane. The small the detector is suspended. Inside, on top of the detector is the fabrication row is on top. You see that part of the detectors are fabricated first at NIST in Boulder in Colorado because they know how to build this radius detector with very with the gigahertz FDM speed electronics, and they will be implanted, and in Genoa will be implanted, and the detector will be finished and made under measurement. Just to give you a simple, very simple schematic of these electronics, very complicated. So this because we collaborate with NIST. This is a very huge expertise in this kind of electronics to have a gigahertz FDM. Gigahertz because we need to have a large bandwidth per detector. We need to have 0.1 microsecond, 100 nanosecond rise time, so we need to work in the gigahertz FDM frequency division multiplexing to read out a large array of 1 kilopixel. Just a few hints about other projects. There is a similar project in German. It's called ECHO project. I am proud because this ECHO project is managed by my PhD student that is now in Heidelberg. So this is a spin-off for our group. They obtained with one of those detectors is a magnetic detector that is different from TS detector. That means they measure the alignment of spin. They are due to the total alignment is temperature dependent, so they have non-directly sense the current. But they measure the magnetic field variation. They have, with a very small source implanted, measured one wonderful spectrum, but the rate is so low that is not usable for making some data about neutrino or about the shape of the lines. So, conclusion. This is a picture shown by John Wilkerson, Neutrino 2012, in which in red you see the typical spectrometer-based, beta spectrometer-based limits since the 50s, sorry, and the scattering on top, and you see, and the calorimetric data that we obtained to two groups, a group of Genova and Milano, obtained in the past. I put some comments on this because the red one data are real experiment with well-known technology. The blue one are proof of the concept. So a few detector made in laboratory prototype, so that cannot be typically mixed in the same picture. Our idea is to go down to the same scattering using this money that we have received by chance from the European Research. The conclusion are written, so I can stop here.
Thanks,
Congratulations to the talks. I have a side comment and a side remark on your slide number 7. It seems that you thought about deeply. 7.
Sorry?
Yeah. As far as I know, Planck people are fully aware of the problem of correlations, and they are trying to sort it out. So that's one of the reasons why the last release of Planck data will be postponed. And my question is about the systematic uncertainty. Which kind of systematic are you referring? Interstellar dust or something like that?
Yes. So as far as I know, the problem of the correlation is not easy, because the problem of the correlation about this different set of data is not easy, mainly on Lyman alpha forest. There is some superimposition of Lyman alpha forest and other kind of measurements. So this is based on assumption. It's very different respect to the experiment that you can do in laboratory. So there's assumption on what is universe local or universe that provide this kind of. Respect to systematic is similar question. So maybe we can talk later on, but a list of effects that must be considered. It's difficult to define systematic in this kind of experiment. It's observation also.
For Olmes, you got an endpoint of 2.8 plus minus 0.05 keV. But for ECHO, the endpoint seems to be 2.5 keV. So can you comment on that?
From ECHO, the question is, if you go in literature, you find 2.55 keV. This is average made by someone about taking account several measurements made also with X-rays and Bremsstrahlung. The question of if you take all the Q value and point value, you find literature all the data from 2.2 to 2.8. My previous measure in 97 we find 2.8, but I don't think this is the correct value because it's based on a QD plot of the intensity of the lines. This is not the Q value of the line or the bright Wiener. Can be very different, the valuation. As I know, ECHO told me, Loredana told me that the first data was 2.8. That is 2.5 was not, I'm not aware of this place 2.5. Maybe Philip can comment on that.
Flavio also did in the measurements from 97 or so, and the results are basically the same. So we are at 2.8, maybe 2,850 EV, but there are a lot of assumptions, mainly on the atomic physics side, that go into it, and there are no solid states effects included in that. So even though the statistic errors on this value of 2.8 is quite low, the systematics we simply don't know yet.
My question or comment was very similar to the one that was said before. At the level of electron volts, it's okay, but if the mass of the neutrino is a fraction of electron volt, 0.1, all sorts of other effects come into play, especially we do not have under control the atomic and the molecular part of the problem, because the energy levels of the molecules are of that order of magnitude that they may interfere. This is the same story as with the Katrin. And so it's going to be very difficult. Also, the calculation of the lines is very difficult. There may be several other contributions, so I want us to be a little bit careful. It's just a comment.
Yes, I can answer a little bit to this comment. It is true, but the technology is different. Katrin is out of the, don't measure the final excitation states. We measure this one, because the ohmium is inside the calorimeter. Unless those effects provide a metastable state longer than the pulse length, the calorimetric pulse length, let's say, are longer than microsecond, the metastable state, those are summed in the full energy emitted. So we measure all the Auger or X-rays emissions, so on, and also all the kind of energy release inside. If this time scale of this emission are lower than integration time of the calorimeter. So that's my comment to your.
Okay. Thanks again, Fabio. And now we are moving to Katrin with Philip.
So we are removing this one. I hope we'll be fine. Okay. I will advise you when we are finding this. Okay. Yeah.
Okay, so after this kind introduction from Flavio on direct neutrino mass measurements, and mainly a main focus on the holmium connected business, I'm here to talk a little bit about the Katrin experiment, the major experiment in this field, I would say. I will give a short introduction to the physics and then go directly to the Katrin experiment and the detection principle it's based on, and then mainly the second part I will spend on the recent or just ongoing commissioning of the main spectrometer and detector section with the subpoints of background and electron optics, and conclude my talk. So we heard that you can determine from beta decay, you can determine the neutrino mass. And if you measure the electron energy, you get a spectrum that looks something like this. And then if you look very closely to the endpoint, you can see a spectral distortion between an expected spectrum for a vanishing neutrino mass or a finite neutrino mass. And since from an experimental reason mainly, it's useful to have a very low endpoint energy, there are two candidates that you can choose to do that. One is rhenium, that was mentioned in Flavio's talk, and tritium is the main contestant in this field, and this is what I will focus on. A very precise type of measurement you can do to determine an electron energy is with the so-called MAC-E filter, the magnetic adiabatic collimation and electrostatic filter. And the idea behind it is that you start your electron at a very strong magnetic field on the order of several Tesla usually, and then you reduce your magnetic field in your spectrometer, and what this does is it transforms transversal kinetic energy of the electron to a longitudinal energy. So the electron, or the momentum of the electron, parallelizes in respect to the magnetic field lines. And then you add electric field that acts as a sharp cutoff for your electrons, and either they are reflected or they are passing through this potential wall. And in the end, you get a sharp transmission for the electrons depending on the emission angle of the electrons, or pitch angle, and your radius in your analyzing plane at the minimum of the magnetic field. And the integrated energy resolution is basically defined by the minimum and the maximum magnetic field in your setup. There have been two successful experiments using this technique, namely the one in Troyes and in Mainz, and both of them are finished for some time now and provide very similar results on the effective electron antineutrino mass on the order of 2 eV. So, and this brings me to the next step in this kind of experiment, namely the Catherine experiment, the calcium-tritium neutrino experiment, an international collaboration of about 150 members from 15 institutions in 5 countries. And the main setup, shown here schematically, is located in Karlsruhe at the Karlsruhe Institute of Technology. The main goal is either the determination of the effective neutrino mass down to 350 milli-electron volts, or at least to lower the 90% confidence level of the neutrino mass down to 200 milli-electron volts, so about an order of magnitude. And beyond the neutrino mass, there are several investigations concerning, for example, sterile neutrinos, or also a lot of technological advances that go in hand with such a big project. And you can divide this experiment in 3 major parts. The source section with the high intensity tritium source, the transport section where the tritium content of the beamline is reduced by about a factor of 10 to the 14, while the electrons are magnetically guided through it, so are not affected by this retention. And in the end, you have the spectrometer and detector section, where where the main energy analysis of the electrons happens and where they are detected. Going through the different parts, the source, the windowless gaseous tritium source, is basically a 10-meter long, 9-centimeter diameter tube where tritium is injected in the middle and then is then left free-flowing in this tube, and with an average activity on the order of 10 to the 11 becquerel. It needs to be extremely stable on a lot of parameters, mainly the inlet pressure, the temperature, and the magnetic field, and still provides the largest source of systematics in the experiment. And the status of it is like that it's currently being manufactured in Bonn in Germany and is expected to be delivered to KIT in August of this year. Then comes the differential pumping section made of 5 major superconducting solenoids at 5.6 Tesla, and in between these magnets there are 4 tow molecular pumps that simply try to pump out the tritium, and this setup will provide a tritium retention of about 10 to the 5. the magnets are already set up at KAT, and currently the magnets are being tested, as well as the beam line in between the magnets is being set up. And the cryogenic pumping section also therefore a tritium retention, in this case up to or more than 10 to the 7. In this case you use the cryo pumping and at 3 to 4.5 Kelvin, and to increase the pumping power actually you freeze argon to the surface of this to increase the surface area and therefore increase the pumping power. And the manufacturing in Genova here in Italy is also in its final steps, and it's expected to arrive in May of this year, so quite soon. Last but not least comes the spectrometer and detector section that consists of two, so a pre-spectrometer and a main spectrometer, where the pre-spectrometer is a pre-filter that reduces the electron current from 10 to the 11 to about only 1,000 electrons per second. And this was used a lot for research and development on different techniques later introduced to the main spectrometer. And then the main spectrometer, what is Katrin so well known for, is responsible for the main energy analysis with an energy resolution below 1 eV. And then in the end comes the focal plane detector made of 148 pixels, a silicon pin diode, with an energy resolution of about 1 keV, but since the main energy analysis happens in the main spectrometer, the energy resolution of the detector doesn't really play a role here. Now coming to the recent measurements. In this part, the spectrometer and detector section made of the main spectrometer, the focal plane detector, were commissioned, and as an electron source, we used angular selective electron gun shown here. And the main concerns were the general hardware, software, and slow control issues with the system, and especially the background and the electron transmission properties. So we're going quickly through the different systems. We looked at the vacuum system, the high voltage system, because for this you need to put the, to act as a McE filter, you need to put the whole main spectrometer at about 18.6 kilovolts. The inner electrode system that covers the inside of the main spectrometer and is mainly there for background reduction reasons. The magnet system, including the main magnets in front and back, and the air coil system that is for fine-tuning of the magnetic field. The electron gun, the focal plane detector, and software and slow control. Just short comment on a few things here. In general, everything worked quite well, but there are two disadvantages in this measurement phase, namely that there were still electrical shorts between the inner and outer layer of the inner electrode. So most of the measurements were done in single layer mode, and the pinch magnet, so after the spectrometer, that provides the main magnetic field was only operated at 5 Tesla instead of 6. But this is solved since a new magnet just arrived at KAT, but unfortunately not in time for the measurement phase. Okay, coming to background. One of the main backgrounds is stored particles that are in the spectrometer that are stored by the magnetic bottle effect. These are mostly created by radioactive decays in the volume or secondary processes like ionization. And unfortunately, one of the main sources is actually we put in ourselves. These are the getter pumps located in the pump ports here. And after some time being stored, these electrons, through scattering or so, lose their storage conditions and are seen as event on the detector. Unfortunately, these processes at the normal conditions can take several hours, So we need first to identify them, what we can do by elevating the pressure in the main spectrometer to, for example, 10 to the minus 8 millibar. And then these thermalization processes are much quicker, and you can easily identify these processes by high multiplicity events, where you see a lot of events in a very short time window, like shown here. So since the main source of this are these getter pumps, you can install nitrogen-cooled baffles in front of them, and the radon atoms are collected on the cold surface and decay there, so don't reach the spectrometer. And the result is that when cooling down the different baffles, so here without baffles, with one baffle, and here with the second baffle, and the third baffle where no pump was located, you can see the rate of high multiplicity events going nicely down, and showing that basically with this setup, the radon background is pretty much negligible. The second part of the main backgrounds are secondary electrons from the vessel wall or the inner electrode, created by either cosmic rays or radioactive decays on the surface. You can have different ways of identifying them, and the countermeasures are magnetic shielding, just from the magnetic field inside the spectrometer, and electric shielding. The magnetic shielding already works quite well, because from the about 75,000 muons that hit the main spectrometer per second, we only see about one event without electric shielding. And from specific test measurements in this asymmetric magnetic field configuration, you can see how effective the electric shielding is. So it goes down by about 2.5 orders of magnitude, but still, as we will see now, we still see some background. In the end, the lowest achieved background was about 400 millicounts per second, with the design goal, unfortunately, about a factor of 40 lower, and some other characterization of this background was actually done. But one needs to keep in mind that the spectrometer was not baked, which means that once we bake the spectrometer again, the pressure will be lower than currently, and this surface conditions inside the spectrometer will change, and this will probably also affect the background properties, hopefully in a positive way. This brings me to my last part, namely the electron optics. So how do electrons behave when going through the spectrometer? A few words towards the electron source we used for this. We basically create monoenergetic electrons with UV light that we shine on a gold surface, and by non-adiabatically accelerating these electrons with non-parallel electric and magnetic fields, you can actually change the pitch angle of these electrons. And we have 4 axes of movement. So here with this huge manipulator, you can cover the whole flux tube, and inside you have also 2 axes to change, as I said, this pitch angle. First of all, the alignment of this electron gun showed that we can basically cover the whole wafer, which is already quite good. So we can cover the whole spectrometer and check for the properties. At low voltage, we were able to see that the energy distribution of the emitted electrons is quasi-monoenergetic with sigma between 50 and 250 millielectron volts. And as expected, this depends on the used ultraviolet wavelength. And at high voltage, so in the usual setup, we're, for example, able to show the angular selectivity. And so here are different transmission functions at different pitch angles. and basically the width between these curves defines the energy resolution of your spectrometer. And in this measurement was 1.2 electron volts, and this is basically, as I said before, the difference between defined by the minimum and the maximum magnetic field that was a little lower than in the usual setup, and therefore the 1.2 eV actually are as expected. And another thing is we moved with the electron gun, we moved down here, so way away from the center, and even with this huge change in position on the wafer and in the spectrometer, the properties didn't change a lot, and you actually see, might recognize 4 curves here, but these are actually 7, because we try to see how symmetric this behaves in order of the pitch angle, and these always 2 curves lie perfectly on top of each other for pitch angles in different directions. So, and this brings me to the end of my talk. I gave you a short introduction over the Catherine experiment, and the experiment is actually in its last step in manufacturing steps, and until this summer all the different parts are expected to be delivered to KAT. And looking a little bit in the future, the second commissioning phase is about to end this weekend or maybe next week. The third commissioning phase is planned for spring of next year, and directly afterwards the physics runs are supposed to start. And concerning the second commissioning phase, we did a lot of test measurements and tested a lot of hard and software components, all without major problems. The background is further reduced compared to the first commissioning phase, but still too high. But the electron optics look very promising and basically as we expect. But a short thing I didn't emphasize enough on, I think, is that these results are very preliminary, since some of the data sets are less than 2 weeks old. So you can actually stay tuned for more results from this measurement phase in the coming future. So this leads me to thank you, the organizers, for the opportunity to speak here, you for your attention, and my colleagues for making this possible at all. Thank you very much.
As you showed in the first few slides, m squared that you obtain is negative, which means that at the end point, the spectrum, instead of going down, it goes up. So this is due to the fact that you are neglecting some other effects. In particular, there are the molecular effects which play a very important role in this. How do you plan to solve this problem? Because the only possibility would be to do atomic tritium, but atomic tritium probably cannot be put there for a long time. So what is your plan on how to solve this problem? Otherwise, you will never be able to extract a neutrino mass which is of the order of electron volts, fractions of electron volts.
Yeah, so I think the results you're referring to are from the Mainz experiment, and I don't know if the Troll's result is also negative in the end, but so one thing is the molecular states, as Flavio mentioned, I think in the end of his talk, from a question as well. The molecular excitations are start on the order of 20 eV, but we are planning to only measure the spectrum 20 eV away from the endpoint. So you need 20 eV to excite the molecules. Okay, I think this is, so I'm not expert in all the parts of this experiment, I'm sorry about that, but I think this is then covered in the systematics we put in. And on the other hand, even if the best fit value is negative, from the statistics point of view, you can still extract a decent upper limit as it was done from the Mainz experiment.
Maybe I can give some help. Yes, the molecular states are the limits of the sensitivity of Catherine due to the molecular final state. So when is emitted, when changed by charge one tritium, you have in molecular this is intermediate that start to oscillate and rotate. And this is the limit of Catherine. It's 0.2 is due to this fluctuation of the state. But the other states are far away. So they have a window. They have a window from the first excited state and the molecular.
So you say background still too high. Can you tell us what are the three strongest sources of backgrounds and how do you plan to attack them?
So the three major backgrounds are, as I mentioned, the stored particles. These have been reduced to because of this introduction of the nitrogen-cooled baffles. And there are actually some active methods. So by changing the magnetic field configuration or introducing an electric dipole inside the spectrometer for fractions of a second, you can pretty certainly get rid of most of the stored particles. So this can further reduce the background. The cosmics-induced backgrounds, or the things from the vessel hull, don't seem to be such a big problem anymore, even though we only operated the inner electrode on single layer wire mode. This is the result from measurements done this Monday, I think, that the second wire layer doesn't influence the background that much. And the remaining part of the background is still under investigation, and there are more curious ideas like outer ionized hydrogen ions on the surface, or some other sources for radioactive particles finding a way into the spectrometer. But yeah, as I said, this is still under investigation and will require a few more weeks to months for the analysis of the taken data from this measurement phase. Okay, thanks again.
And now we are switching to project 8. 5 minutes.
Okay, great. Thank you. All right, so I'd like to thank the organizers, first of all, on behalf of the Project 8 collaboration, for giving me a chance to come here and tell you about our experiment and the first results, and then also from more recent progress that we've been making. So we've had a great introduction in the last two talks to using beta decay, and in particular tritium beta decay, to measure the effective neutrino mass, and so that is also the goal of Project 8. But we want to look at whether there's a way to go beyond what Catherine is capable of. This is the shape of the spectrum from a 0.2 eV neutrino mass, but there is another order of magnitude to go before you could get down to the lower limit that is set by neutrino oscillations. So the goal for Project 8 is to come up with, or to use a new technique to be more sensitive to the neutrino mass, and in particular that technique is called cyclotron radiation emission spectroscopy, or CRESS, and the basic point is to use the cyclotron radiation from the beta electrons in a magnetic field to measure the energy of those electrons. So We made the first direct measurement of single electron cyclotron radiation last June, and showing that this will in fact hopefully work. And we are currently in the process of looking at improvements to both the energy resolution and the statistics in the hope of making our first tritium measurement later this year. Just measurement of the tritium spectrum, not quite the neutrino mass yet. So the way the technique works is that you have some volume of tritium gas in a nice uniform magnetic field, and you're going to have the electrons spiraling around the magnetic field lines emitting cyclotron radiation, and we want to detect that radiation. And the reason this is useful is that the frequency is inversely proportional to the total energy of the electrons. And so here in this plot, for example, is the cyclotron frequency as a function of electron kinetic energy for approximately a 1 Tesla magnetic field. And this is around 25 or 26 gigahertz. And I've just highlighted here the tritium beta decay endpoint at 18.6 keV. We're currently using krypton 83M, which has some conversion electrons at 17.8 and around 30 keV. One other thing to define is the pitch angle of the electrons, which is the angle between the magnetic field and the momentum of each electron. This becomes important because there are some other terms in the cyclotron frequency that are dependent on that pitch angle. This is for close to 90 degrees, which is the pitch angles that we mostly observe. And then also in the total power that's emitted, and we're looking at about 1 femtowatt power going into the cyclotron radiation. So in a little more detail, our experiment actually consists of a rectangular waveguide about 4 by 11 millimeters, and we're using this krypton 83 gas, as I mentioned. The radiation couples to the modes of the waveguide, and we read it out on one end with a low noise amplifier. We also have a small little magnet coil that produces a small dip in our magnetic field, and this gives us some axial trapping of the electrons, so they just move back and forth in that little trap, and we can observe them over an extended period of time. This is a little more detail of what our prototype experiment looks like. The gas cell is down here inside of our magnet. We have the waveguide going up to our amplifiers where we read out the signal. This is the picture of the waveguide, or the insert that we saw before. We have the gas lines that come down to our gas cell in the center. The waveguide going up is tucked in the middle there. And then this dark band is our small trapping coil. When we read out our data, we're looking at spectrograms that are the power as a function of frequency and time. So each row here is a single power spectrum, and we're looking at how that evolves in time. And we want to see some large amount of power deposited in some finite amount of time, and that would represent a single electron. So last June, we saw our first events. So here's an example where we have a number of tracks all in a row. There are some very interesting features here. On the left is where the electron is initially trapped, and then you can see a number of tracks sort of head to tail, and this occurs when the electron actually scatters off of one of the residual gas atoms or molecules in our gas cell and comes out with a slightly different energy and therefore a different frequency. You can also see that these tracks aren't flat. They go up in frequency, and this is a result of the electron losing energy to the cyclotron radiation. So once we identify single electrons, we can make a spectrum of our candidates and show when we turn the trap on or off that we do indeed see these peaks of electrons, and when the trap is on but not when it's off. Returning for a second to this first event, this was the first thing we saw, but it's not actually the entire event. This particular event was quite remarkable. If we zoom out a little bit, there are about 15 other tracks here that I'll highlight because they're hard to see. So this was really a remarkable event to have so many tracks. But one thing you'll notice is that it actually jumps up and down in frequency as it goes along. And this is a result of the fact that the cyclotron frequency not only depends on the energy, but also the pitch angle that I mentioned. And whenever a scatter occurs, it changes energy and pitch angle, so you can move in both directions. So we want to be very careful to make sure we, of course, identify which actual track is the first one, so we know so we get an accurate measurement of the initial energy. So we can make a spectrum from these measurements. The background plot here shows the full spectrum with the 17.8 keV, 30, and 32 keV electrons. The inset is zooming in on the 30 keV electrons. Our initial measurement had a full width half max of about 100 eV. We were able to improve that by reducing the trap depth. So here we went down to 10 eV just by making the trap a little shallower so that the electron was experiencing a smaller variation in magnetic field. To move forward, though, we would like, so we've demonstrated that the technique works, and we're going to work on improving our energy resolution in the hope of soon making a tritium measurement. One way we want to do that is to change the geometry of our trap. So we actually first successfully did this about a month ago using 2 coils producing little bumps in the magnetic field. This gives us a larger volume and a more homogeneous magnetic field, and we successfully improved the full width half max resolution from 140 eV with our initial trap down to 60 eV already, just with half of the bathtub trap actually. The other thing we want to do is actually to disentangle the angle and the energy, and we'll use the axial frequency of the electron as it moves back and forth in the trap to do that, because it also has a dependence both on the angle and the energy, and that produces sidebands in our signal, and if we can detect these sidebands, the separation from the main peak is actually the axial frequency. And so just 2 weeks ago we first did that. This is an example of averaging along a track where you can see a nice tall main peak, and then by averaging over the track you reduce the noise and you can see the 2 sidebands off of there. Once you know where these sidebands actually are, you can go and look for them. Here's our nice strong main peak that's fairly easy to find, and if you know where to look, you can sort of see this very faint sideband there that would otherwise get lost in the noise. So this was very preliminary just from a couple weeks ago. So that brings me to the next steps for Project 8, which is to move to tritium. Our first attempt is going to be with a sealed waveguide cell that basically keeps most of the system the same and just replaces our gas system, which we think we can accomplish by later this year. And then we want to move to a larger source that will help improve the statistics by having more tritium. And we want to use a phased array of patch antennas that takes advantage of more of the 2-inch volume, 2-inch bore of our magnet. So that brings me to the end, and I'll just put up the summary points that I had before. We've now demonstrated this technique of cyclotron radiation emission spectroscopy and made the first observation of single electron cyclotron radiation, and we are now pushing very hard to get our first tritium measurement by later this year. Thank you.
Thank you for the interesting talk. Questions? Okay,
There's one question.
You have shown sometime final sensitivities. Do you keep these projections that you would explore the inverse hierarchy at some point, and you have some, I guess it's a guess, it will be when this will happen, and
we have shown that we think we can get certainly eventually down to the inverted hierarchy region. I'm not sure exactly what the timeline for that would be, and it's not tied to any very specific design that we'd be looking at, but it's certainly feasible to get down fairly low in, I don't know, 5-10 years, something like that. How low? So very approximate projections could get us down to like 0.04 or 0.05 eV with, but that would require an atomic gas source, so atomic tritium source. So that in and of itself has many challenges.
Thanks. Now we are moving towards Eccola qua, ok. Ok. Ok.
So we now shift to double beta decay, and with some recent results on calculations for double beta decay. So double beta decay is a process in which a nucleus X goes into the nucleus Y, emitting two electrons or positons and usually light particles, other light particles. Here's an example of germanium-76 going to selenium-76. And for processes which are not allowed by the standard model, the inverse half-life can be, to a very good approximation, split into a phase space factor, which depends on atomic physics, and nuclear matrix elements, which depends on nuclear physics, and whatever physics is beyond the standard model. But concomitant to those processes, there are processes which are allowed by the standard model. And in this case, the half-life can be split into a phase space factor and nuclear matrix elements. There is, of course, no dependence on whatever physics is beyond the standard model. There is only one exception to this, and this is the case of neutrinoless double electron capture. This process is forbidden by energy momentum conservation, but it can occur under resonance conditions. And in this case, the inverse half-life is given by this expression here, which again a prefactor, a matrix element, the physics beyond the standard model, and then a resonance factor. So this is the situation in which the energy of the initial state precisely matches the energy of the final state, because then in that case we can satisfy energy and momentum conservation. However, this requires a precise matching, which is rarely to occur, and so it can only occur through the tail of the width of the final state. And so to calculate this accurately, we need to calculate very accurately what is the so-called degeneracy parameter, which has to do with the energy of the two electron holes which are left in the final nucleus, and plus some other corrections. So, as we saw before, there are two main ingredients to extract whatever physics is beyond the standard model. One is the nuclear matrix elements, and one is the phase space factor. So the nuclear matrix elements can be written in the following form by putting in front the axial vector coupling constant GA, and this is squared because there are two vertices, and then here they're written as the gamma of Teller, and the GA has been put in front, so this is gamma of Teller, that's the Fermi contribution, and there is also an induced tensor contributions. Now, several methods have been used to evaluate the nuclear matrix elements, which are here indicated, some of those. Now, major progress has been made in the last few years in calculating those nuclear matrix elements, in particular in the so-called interacting boson model 2. The nuclear matrix elements have been calculated for all processes, and so the calculation has been completed and is available upon request. Some of you may be interested in those. There is a list of reference in the Appendix A, and a list of the numbers also in the Appendix A. Now, for zero neutrinos, two scenarios have been considered. One is the emission and reabsorption of a light neutrino with mass much smaller than kilovolts or MeV, and two, emission and reabsorption of heavy, hypothetical heavy neutrinos with masses much larger than GeVs. So here is a schematic sketch of what is going on. The neutrino is emitted here. If it is a Majorana particle, it's its own antiparticle, so it can be reabsorbed by the other nucleon, emitting another electron. So this is, I will call this M light, with mass of neutrino much less than 1 keV. Now, since the mass is much less than 1 keV, so the order of fraction of electron volt, this is like massless, and so this looks like a long-range interaction. In other words, the neutrino is emitted at one end of the nucleus and is absorbed essentially at the other end. I will discuss this factor F in a moment in the next transparency. For every neutrino exchange, the mass of the neutrino is very large, so essentially the neutrino is emitted at one point and reabsorbed at the same point. So this is a very short range. So to remind you of a little bit of the theory of double beta decay, so here is the dependence on the average neutrino mass for light neutrino exchange. That factor F, which has the physics beyond the standard model, turns out to be proportional to the average neutrino mass defined as this combination here of the three masses of the three neutrinos 1, 2, and 3. And here is the Fourier transform of the neutrino potential in this case, which, as you can see, is essentially 1 over p squared, and 1 over p squared is Fourier transform of the Coulomb potential due to the fact that, in effect, the neutrino is massless, and so the interaction is very long range. So, as we have seen in the many previous talks and last few years, we have had some information on the mass of the large neutrino, mass differences, and then mixing, and with two possibilities of the normal and inverted hierarchy with the different hierarchies of the neutrino masses 1, 2, and 3. The average neutrino mass can be written in this form in terms of the mixing angles and the mass differences, and fit to oscillation experiments by Gianluigi Fogli and others already in 2008 indicated values of the mixing angle given here and of the difference in masses given there. With the Diabet result, there is a small change into this fitting formula. Now, if one varies then phases phi 2 and phi 3 from 0 to 2 pi, this gives the values of the average neutrino mass, which is consistent with oscillation experiments, and so it gives constraints on the neutrino masses for light neutrino exchange. And this is plotted in a plot which is, was introduced by Francesco Vissani, and it is here with the inverted hierarchy. The expected possibilities are here, and with the normal, they are here. So for scenario number 2, every neutrino exchange, the dependence on the average neutrino mass is just the opposite. Now this F is proportional to the inverse average neutrino mass, which is given there, and then I put some scale here, putting the proton mass as a scale instead of the electron mass that we did before. But also the other main difference for every neutrino exchange is the Fourier transform of the neutrino potential is a constant, because essentially it is a contact interaction. It occurs just at one point due to the fact that the mass of the neutrinos is very large. Now, to have constraint on the average inverse mass, this is model dependent, and we have used here a recent paper in which the factor F can be written in the following form: the mass of the W boson here divided by the mass of some hypothetical WR bosons, which has been put here at 3.5 TeV, and then you have the mass of the proton divided by this average mass. So this parameter is in the literature is called the lepton violating parameter eta, and then constraints on eta can be converted in constraints on the average heavy neutrino mass by this simple formula. So now here are the most recent results for the nuclear matrix elements for light neutrino exchange. For 3 of the different calculations that have been done so far, the IBM2, the quasi-particle random phase approximation, and the shell model. Now, some of you may recall that years ago there was a large discrepancy, even by factors of 10. This has now been reduced considerably, And now the uncertainty in the nuclear matrix element, if you consider this uncertainty difference between the different calculation, is less than a factor of 2. Also, another interesting aspect is that while the QRPA and the IBM2 seem to be relatively close to each other, the shell model results are systematical, at least in this nuclei, lower than the others. But this uncertainty has been considerably reduced now relative at what was a few years ago. So that's good news in a way for the experiments. Now here is the most recent results for heavy neutrino exchange. Note the scale is different. Now the nuclear matrix elements are larger in this case. The physical reason for this is short range correlation increased those matrix elements. So the matrix elements are larger, but still there is a spread between the different values, and in factor there's a difference of a factor perhaps 2 or 2.5 between these two sets. So this concludes my brief discussion of the nuclear matrix elements. Now for the phase space factor, these were calculated many years ago by Doi and others. There is also a calculation in the book of Focal, but these calculations use an approximate expression for the electron wave functions of the nucleus. And recently these have been recalculated with exact Dirac electron wave functions, and also including electron screening by the electron cloud. And these are now available. In fact, they've been already used by several of the experimental groups to analyze data. They are available either by writing to Kotila or extracting them from the nuclear theory. I will not say much about phase space factors because it's not the main purpose of this talk. And instead, I will proceed with the main important part of this talk, which is this question of quenching of the axial vector couplings constant. So the results in the previous slides have been obtained with the axial vector coupling constant used the free value of 1.269. However, it has been known now for more than 50 years that in single beta decay, single electron capture, and also nowadays in 2 neutrino double beta decay, the GA is renormalized in models of nuclei. That's a fact. There are 2 reasons for this. One is that all calculations are done in models with a limited model space. Nobody can do a calculation with an infinite Hilbert space, so calculations are done in a limited model space. And also that there is omission of non-nucleonic degrees of freedom like delta and star and so on. So for each of these models, one can define an effective coupling constant by writing M effective as the ratio here as the square, because it appears twice, GA for the 2 neutrinos, or as GA effective or GA for the single beta decay or single electron capture between the calculation and the experiment. Now, what information do we have on this GA effective? Now, for each nucleus, GA effective can be obtained by comparing the calculated and measured half-lives for single beta decay and for 2 neutrino double beta decay. So here are the results for the values of 2 neutrino effective obtained from experimental half-lives, because now 2 neutrino double beta decay has been measured in about 11 nuclei here as indicated here. So here's the values of the neutrino effective matrix elements. They are large in molybdenum. They are relatively small here. And the smallest of all value, the value of xenon, was measured by EXO just a few years ago, and is here this very, very small value. There is also an old measurement on uranium, although uranium cannot be used for double beta decay for other reasons, but here are the nuclei for which we have information for 2 neutrino double beta decay. So now if we compare the experiment with the model calculations, as a function of mass number, we can extract the effective coupling constant here, Ga, for those nuclei. And there are here two sets. One is the extracted from the shell model. Here, the free value is up here, 1.269 is up there. So these are the values extracted from the calculations with the shell model. And if one wishes, if he wants to parameterize with a smooth A dependence, we have used this smooth dependence, these parameterizations here for the A dependence. It falls as a power of A, but with a relatively small exponent. And here are the value extracted from the interacting boson model. And here is a parameterization of those. Of course, around this smooth parameterization, there are different values which depend very much on the nuclear structure. And so in germanium and selenium, actually Ga is slightly larger, while it's slightly smaller in molybdenum and cadmium. But the main point, the bottom line of this is that the values of Ga effective obtained in the interacting boson model are of the order of 0.6, 0.5. Those extracted from the shell model are of the order of 0.8 or 0.7. So Ga effective has also been extracted in QRPA very recently by Sukonen and others with the values similar, and also a few years ago by Fessler, Fogli, Lisi, and Rotunno, Shinkovic, and with a value of 0.7. In some earlier papers, QRPA paper, it is claimed that there is no renormalization of Ga. However, this claim is based on results where the renormalization of Ga is transferred to a renormalization of the free parameter GPP, which is used in the calculation and then is adjusted to the experimental to new values. So again, QRPA indicates a quenching of the order of 0.7, 0.8. So now, once we have seen that we have this quenching, the question is, what is its impact on double beta decay? So, unfortunately, the axial vector coupling constant Ga appears to the second power in the nuclear matrix elements. And here is where it appears for for 2 neutrinos. For 0 neutrinos, it also appears here in this combination. But if it is second power in the nuclear matrix element, it is fourth power in the half-lives. So the normalization of Ga has a tremendous effect on expected half-lives for double beta decay, because the results of the previous slides then should be multiplied by 634 to have realistic estimates of expected half-lives. And similar discussion has been done recently by Robertson and also by Stefano De Loro, Marcocci, and Bissani, and there is a poster upstairs to discuss this in further detail. So, now we have to understand this question, whether Ga is normalized for 0 neutrino double beta decay as much as it is for 2 neutrino double beta decay. This is in the course of discussion right now. The difference is in 2 neutrinos, only one multiple contributes, the gamma of Teller multiple, while for 0 neutrinos, since it's a long-range interaction, all multiple contributes. And this may be, some of this could be unquenched. However, even for 0 neutrino, gamma of Teller dominates. And therefore, our present current understanding is Ga is normalized in 0 neutrino as much as 2 neutrino. So there is an attempt to try to investigate this both from the experimental point of view by measuring matrix element to and from the intermediate of the nucleus in 2 neutrino double beta decay, and also theoretically by evaluating using effective field theory the effect of non-nucleonic degrees of freedom. Another question is whether or not the vector coupling constant is normalized in nuclei. Now, because of conserved vector current, the mechanism 2 cannot contribute. The omission of non-nucleonic degrees of freedom cannot contribute. However, mechanism 1, which is limited mode states, could contribute, and if so, the ratio GV over GA may remain the same as the normalized ratio. No experimental information is available at the moment, but it could be obtained, and there is an attempt now to extract some of this information for charge transfer reactions, both helium-3T and helium-2, but also there is an interesting new idea to extract this from heavy ion double charge exchange reactions at the Laboratori Nazionali del Sud in Catania. So, conclusions of this talk is that the major progress has been made in the last 2 years to narrow down predictions of zero neutrino double beta decay to realistic values in all nuclei of interest. All nuclei now have been calculated. All double beta decay nuclei have been calculated. Now, here are the current limits on the neutrino mass from for light to neutrino exchange with the free value GA 1.269, the nuclear matrix element of IBM2, and the phase space factors of Kotila and others. And so here is again plotted in this plot the result with the free value of the GA. In this plot there is also here a dot, which is the claim by Klaptor of having observed the double beta decay. And the best limit at the moment with these values are Kamelan-Zen and EXO, with a limit of about less than 0.2 electron volts. And then there is Gerda and others. Quore will come down somewhere here. But this is at the moment the current situation. So, summarizing this, with the GA 1.269 for light neutrino exchange, only the degenerate region can be tested in the immediate future. The current best limit with the GA, this value, is from EXO and Kamelan-Zen, and this for the mass of the neutrino about 0.2 electron volt, less than 0.2 electron volt. Exploration of the inverted region may require multi-ton experiments. For heavy neutrino exchange, the limit is, as I said before, is model dependent. In the model I mentioned before, the current best limit, again from EXO Kamelan-Zen, is for the mass of the heavy neutrino greater than 257 GeV, but again it depends on the value of the assumed mass for the hypothetical WR boson. If this is 1 TeV, then this is a factor of 3 to the 4th power, which will push the limit of the neutrino, heavy neutrino mass to values above TeVs. So, progress has been made, but there remains a major question, which is the value of GA. And 3 possible scenarios are GA 1.269, which is what is quoted before, GA equal to 1, which is the quark value, and GA equal to this value here, which is here called maximal quenching. So these are the 3 possible scenarios. If GA is normalized to these values of 0.8 to 0.5, all estimates for half-life should be increased by a factor of 6 to 34, and the limits on the average neutrino mass should be increased by a factor of 2.5 to 6, and making it impossible, in fact, to reach in the foreseeable future even the inverted region. And here is a plot again, the limits taken from EXO in 136 xenon decay, with the GA equal 1.269, we are at 0.2 at the moment. If GA is 1, we are up here at 0.8, and if GA is 0.5, we are here at 1.2 electron volts or something like that. So this effect of the value of GA is going to have a tremendous consequence on planned or current planned experiments in neutrinoless double beta decay. Now, what are the possibilities to escape this negative conclusion? Well, one possibility is the neutrino masses are all degenerate and large. We are somewhere up here in that. But this possibility will be in tension with the cosmological bound on the sum of neutrino masses that we've seen already in several talks in the previous days. Here I have a value of 0.23 from Planck, which will put the limit here. So it will remain then only this tiny window possible for the neutrino masses. Of course, this is model dependent, so it depends on what ingredients are put in order to put this limit, but certainly this will cause a problem in case the masses are degenerate and large. So other possibilities that both mechanisms, light and heavy exchange, contribute simultaneously, are of the same order of magnitude and interfere constructively. So in this case, the inverse half-life is just a phase space factor, and then we have the matrix element for light neutrino multiplied by the average mass of the neutrino plus matrix element of heavy neutrino, and then divided by the mass of the heavy neutrino. This is possible, but will require a fine tuning between these two. The phases have to be in such a way that they will add, and also that they will have to be of the same order of magnitude. It will give us an improvement of a factor of 4 in the inverse half-life. The third possibility, which again has been discussed already before, is that other scenarios, other mechanisms contribute. In particular, there could be possibility of the emission of a majoron here, or sterile neutrinos could contribute. So we are then at the present time considering these two possibilities. For majoron emission, the inverse half-life, this scenario is called 0 nu beta beta phi decay, is given by this expression. So here we have the phase space factor for this process, then the nuclear matrix elements, and then the effective majoron coupling constant here. Now, the nuclear matrix element in the case of majoron emission are the same for scenario 1 and 2. Because GA will appear there as well at the two vertices where the neutrino is emitted and where it is reabsorbed. We are recalculating at the present time the phase space factors to provide a more realistic calculations with relativistic effect contained, and also electron screening. So this will be available soon, and then we'll be able to put some limit on the effective majoron coupling constant. The fourth possibility is sterile neutrinos. Now, it depends on how many other neutrinos you have there, for neutrino number 4, number 5, number 6, and whether the range is keV, GeV, or it is electron volts or less. This, as you know, is being quite at the moment discussed a lot. Now, for this, the phase space factors are already available. For this scenario, we need to recalculate the nuclear matrix element, because the nuclear matrix element depends very much on what is the mass of the exchanged particle. The two cases we have considered so far is the case in which the mass is essentially 0, light neutrinos, or infinity, which is heavy neutrinos. For intermediate masses, we have to use a different form for this effective neutrino potential, which will contain the neutrino, effective neutrino, sterile neutrino mass here. And then we can calculate all of this. Fortunately, all the formalism is already there in place, so this calculation will be available soon as a function of the neutrino mass, and the PSF are, for these scenarios, are therefore available. So finally, my conclusion is that no matter what the mechanism of neutrinos double beta decay is, its observation will answer the fundamental question, especially whether neutrinos are Dirac or Majorana particles, because the process can occur only if those neutrinos are Majorana particles. Also, what is the absolute neutrino mass scale, and how many neutrino species are there? Thank you very much.
Thank you for the exhaustive discussion here, and please, first, then Carlo.
I didn't quite, I'm not expert in this, but I didn't quite understand what are the ambiguities on the renormalization of the coupling? In other words, does it depend on physics beyond the standard model, or?
That's not, it depends just on nuclear structure.
It just depends, so it could be, it doesn't tell us any information on the standard model or not?
No.
Thank you.
And in fact, that's the effort now that is going on, is trying to understand whether we can pin down the nuclear structure to the extent that we are reducing that.
Yes, for the normalization of GA, you say that one of the reasons is the limited model space. But in the case of two neutrino double beta decay, you have only one intermediate state. So what is missing there? You can, for example, in the shell model, they can calculate exactly, well, with some approximation, but high precision, the intermediate state. So what is missing? Why they need this renormalization of GA?
Yeah, it's that no matter which model, the space is always limited and some states are missing. And to this effect, there contribute many, many states, not just one state or a couple of states. And even if you go to very large spaces, still you have the proper normalization. As you have seen in the shell model, you have results in this heavy nucleus of the factor of 0.8 or 0.7.
But you say that in the two neutrino decay, you have only one intermediate state.
And even that one is reduced by 0.8 or 0.7. Okay?
Yeah,
it's an unfortunate thing. I wish I could not do this, but we have to say what the truth is. I cannot ignore it, because there was in earlier places, I had one person who said, I asked that person, why didn't you say this question about GA in the past? And the person said, not to scare the experimentalists. This is not an answer.
You presented the scenarios of the light, the heavy, the Majoran, and the sterile. On one observable, which is the cross-section, if, for instance, you measure the angle between the two electrons, do you, you should be, in principle, be able to separate the scenarios. Isn't that true? You should have a different angular distributions, no?
True, but I did not have time to do all that.
But it is true.
We calculated all the different angular distributions and so on and so forth. Those are available.
Those are available.
Also, there are questions concerning the phases, whether you can get the phases with different, if there are different contributions. And another important point is that it would be important to do the measurement in different nuclei, not just in one single nucleus. And that's why having germanium and tellurium is a very important zero.
Okay. Thank you,